Okay, so today we are talking about how to name alkenes and alkynes following the IUPAC nomenclature rules. How do we name alkenes? How do we name alkynes? Okay, so an alkane is what we learned the past couple weeks, right? An alkane has carbon-carbon single bonds, yes? The formula for an alkane is C to the N, H to the 2N plus 2, right? That's the generic formula for any alkane. And the ending ends in ane, right? C double bonds all down the chain. Whether it's in a ring or linear, they're all carbon-carbon single bonds. An alkene has the generic formula C to the N, H to the 2N, right? Why did we drop the plus 2? Right, you've lost these two hydrogens and created a double bond here, right? So that's the difference in the formula, 2N plus 2 versus 2N. And the ending is ene. Notice A-N-E ending, E-N-E ending. Just one letter difference. That's where things start getting really fun in the spelling department. And then an alkyne is C to the N, H to the 2N minus 2. Again, now what happened? We've lost two hydrogens again and created a triple bond here. Right, so it's 2N minus 2. So 2N plus 2, 2N, and 2N minus 2. And the ending of the parent chain will end in Y. So ine, ene, and ane. Right? Alkane, carbon-carbon single bonds. Ethene has at least one double bond, and an alkyne has at least one triple bond. Okay, so there's going to be at least one triple bond. There's going to be at least one double bond. Are they all going to be double bonds? No, but there's at least one. Are they all going to be triple bonds? No, there's at least one. Okay, now this is something that we talked about in alkanes, right? We can have conformations made by rotating because these carbon-carbon bonds rotate freely, right? We have the staggered and the eclipsed in the alkanes, right? We rotate those freely. That's like standing on one foot versus doing a handstand, right? But in an alkene and an alkyne, you don't have that free rotation anymore, okay? You can't just freely rotate it. It's not going to happen anymore. That double bond locks you in place, okay? So you do not have conformations, but you do have isomers, okay? You're going to have isomers in alkenes. We'll talk about that today. And then in a alkyne, it's linear. These are going to be linear molecules. It's going to be linear during the double bond here too. Right, so here's, again, showing that linearity. Right, we get that zigzag going through the alkane because of the tetrahedral molecular geometry. When you have a double bond, though, that flattens it out. So the molecule is actually flat during the double bond, and then it can go back to being zigzag again. And it's flat during the triple bond, but it goes back to zigzag once you're out of that. Okay, so we call it planar. Planar is the word that we use for flat. And that's going to be a big part of what we talk about in biochemistry when we start talking about that portion of the course, right, the elementary biochem portion of the course. We'll look at how that double bond makes biomolecules have different properties. And so the double bonds are going to create different IMFs than the single bonds did. And just like we saw with alkanes, with alkenes, as the molar mass goes up, the boiling points are going to go up as well, right? But introducing those double bonds will create new IMFs because notice this is a linear part now that wasn't linear to begin with, right? This is going to stack differently than this. So we are going to have new IMFs when we introduce double bonds, which means same trend though as we already saw. As you increase the number of carbons in the chain, the boiling point will go up as well. All right, so we're going to do alkenes first. And once we understand alkenes, then we'll come back and do alkynes. So there's got to be at least one carbon-carbon double bond to call it an alkene. So this is what I just said. 2N plus 2 is alkane. 2N is alkene. Okay, and this is again showing you what it looks like. The molecule is planar around that double bond, right? This is two orbitals that are free to rotate, but during that pi bond, that's what that's called, we don't have that free rotation anymore. That's electron density above and below. All right, this is again just showing that we don't have that free rotation like we do in the alkane. We do have the free rotation in the alkane. We don't have that free rotation in the alkene because of where the electrons are hanging out. So how do we name alkenes? How do we name alkenes? Carbon number 1 is the carbon closest to the double bond. So even if you have a double bond and a substituent, okay, the double bond ranks higher than the substituent in terms of priority. So let's pretend I could count from the left and get 1, 2 to the double bond, or I could count right and get 1, 2 to the substituent. Who am I going to count to give priority to? I'm going to count to the double bond over the substituent. Okay, so you always want to give the double bond the lowest number, and then any substituents, we'll worry about them secondary. And then just like everything else we've done so far, substituents go in alphabetical order. Okay, and then there are 2 options. I'm just going to add this to the slide right here because I know it's in there later. There are 2 options for your suffix. Okay, now your textbook presents it one way, but then other textbooks present it the other ways, so I will accept both. Okay, you can split the suffix or keep it together. So let's do an example. I'm going to just draw it on the screen. You can split the suffix or keep it together, which I know sounds really strange for me to say, but when you see an example, I think you'll see what I'm talking about. All right, so let's pretend that we've got okay, so are we going to number from the left or from the right? 1, 2, 3 gives the priority to the double bond. 1, 2, 3 gives the priority to the substituent. We want to number from the left, right? 1, 2, 3, 4, 5, 6, 7. So the substituent still goes first, okay? So it's still 5-bromo. And now that double bond could be anywhere in this chain, right? It could be between carbons 1 and 2. It could be between 2 and 3, 3 and 4, 4 and 5, right? It could be anywhere. So I've got to tell the reader where my double bond is. And so here's where I say split the suffix or keep it together. If you're doing it using this method, you would call it 5-bromo. And then this is a 7-carbon chain, right? So you'd say hep. And then you'd say 3-ene. Put it in between the word heptene, you'd stick the 3 there in the middle. Your textbook does not present it this way, okay? Here's what your textbook says. Your textbook writes it as 5-bromo, 3-heptene, okay? So I don't care which method you prefer. Some textbooks present it this way. Some textbooks present it this way. They're both acceptable, okay? So you pick the one that you like. Either split the suffix or keep it together. I really don't care. They're both acceptable. And your textbook is going to do it this way, but lots of other texts are going to do it this way. So I always show you both, so when you go on and take full organic, you're probably more likely to see this, but you might see this too. Okay, well, most elementary organic students prefer this method just because you don't have a number right in the middle of the word. That rolls off the tongue a lot more easily than that does. Okay, but I'll accept either one for your suffix options. Does that make sense? So you can do it either way. I'm happy regardless of your decision there. And I'm pretty sure your online homework will accept both as well.
So you number from the other end, but bromo still comes first.
Right, yeah, because it's a substituent. And so the suffix is just on the parent. Yep, yep. Okay, so here, let's just name these both ways. Let's just do it on the board. Here we have no substituents. Right? No substituents on any of these, so there's not going to be any substituent. We're numbering from the left or the right? Right. So this is going to be 1, 2, 3, 4. So let's do it both ways. If we're doing it, keeping it together, what would that be?
It would just be
1, and that's a 4-carbon chain. Well, this is a 4-carbon chain, so it would be butene, right? Because a 4-carbon chain would be a butane. We change the suffix to ene. So if we keep it together, it'd be 1-butene. If we split it, it'd be but-1-ene. It's telling the reader it's a 4-carbon chain with a double bond between carbons 1 and 2. Does that make sense? Let's do this one. We can number from the left 1, 2, 3, 4, or we can number from the right 1, 2, 3, 4. Either way, you're going to get the same answer. Right? So let's just number from the left since most people read left to right. Okay, if we keep it together, what would the name be? Right? Or what's the other option that you could have? Right. That doesn't flow very well off the tongue. That's why a lot of students prefer this. But just know that the other option is equally acceptable. And then if we had any substituents, we would put them first. So if we had, let's pretend that this is a 2 and this is a chloro right there, right? We would say 1 chloro 2-butene, or 1 chloro but-2-ene. Okay, make sense? So I'm pretty sure your online homework will accept either version that you choose to go with. I'm almost certain that it accepts both. Now these two are structural isomers of each other, right? All right, take a second and name these using either method that you prefer. I'll pause it and let you try. All right, let's go over these. We'll name it both ways just for practice. And just so you know, technically the molecule is flat during this part, right? If you were going to draw this technically, let's first number, right? We're going to number from the left or from the right? From the right. 1, 2, 3, 4, 5, 6. Now, if you want to draw this thing technically, 1, 6, 5, 4, 3. It gets flat right there. 2, and then 1, right? Because it's technically flat during the double bond. But if you want to just draw it like that, that's okay. But just know that the molecule is technically flat during that double bond. Okay, it gets linear. So, what's the name of this? Hexene, right? Or you could have called it hex 2, 8, right? And then how do we number this one? Does it matter? 1, 2, 3, 4. 1, 2, 3, 4. You're going to get the same answer either way. Right, so this is what? Or octene. Or what? Oct-4. Right. And again, if you were drawing this, if you wanted to be technical, you would draw this part flat, right? Because during the double bond, it is technically linear. However, if you want to draw it in skeleton and just slap the second one on there, that's fine. And I'm pretty sure the online homework won't count you wrong if you drew it like that. If you didn't make this part flat, I don't think the online homework will mark you wrong for that. And so once we start adding, I'm just going to leave that down because I think the next one has substituents. Yes, right? So when we're doing substituents, right, we're numbering to give the double bond the priority. If we were going to split the substituent, 4-methyl, 2-pentene, what's the other way we could write that? 4-methyl, pent, 2, right. Okay, both are acceptable. Like I said, most students prefer this because it keeps the word together, but I'll accept both. It all depends on the book. And our intro organic book keeps it together. Okay, so name this one. I'll give you a second to try it. Let's see how you did on this one. I don't know why I even bother putting the screen down because I'm just going to end up writing on it again. Let's put this in a Word document. Whoa, that's big. I like being able to write on the board. There we go. All right, how do we, first we need to identify the longest parent chain. Now the longest parent chain must include the double bond, okay? Because if your longest parent chain went 1, 2, 3, 4, 5, that would exclude the double bond. And that's the highest ranking thing, so obviously we can't do that. Right, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right, it's not going to matter. 1, 2, 3, 4, 5, 6, 7. Is that going to make a difference between here and here? No, it's not. All right, so let's just name it. Let's just go linear. 1, 2, 3, 4, 5, 6, 7. So the name here would be what? Be careful.
Oh, 3-ethyl.
Right, alphabetical. 3-ethyl. Then what? 6-methyl. And then what?
3-heptene.
Right, 3-heptene. If you were splitting it, it would be the same thing. Hept 3-ene. Good on that one? All right. Okay. Now, when you're looking at the way the alkene is drawn, remember when we were doing, just going up and down, up and down. Remember when we were doing isomers last week, we did cis and trans in a ring? We can have cis and trans in double bonds too. Now, when you're looking at this, you can't see cis and trans, right? You can't see it. But look at this. Now we get a better appreciation for what this looks like in 3D space, okay? Because if we actually spread this out and make it linear during that double bond, we can actually see how these things are oriented towards each other. And so you can get a lot more information based on how it's drawn. So there are 2 structural isomers here. These both have the same formula. One is cis, one is trans. So how do we diagnose this? You look at the double bond and you compare what's on both sides. Which is bulkier, this or this? Obviously this part is. Which is bulkier, this or this? This is. So if the 2 bulky pieces are on the same side of the double bond, we say it's cis 2-pentene. And then when you're comparing, again, if the bulkier pieces are on opposite sides of the double bond, we call it trans 2-pentene. Now you'd have to draw it like this to show cis and trans. Okay, you've got to show this based on how you're drawing your molecule. Do we see how to tell the difference between the cis isomer and the trans isomer? Will these have different boiling points? Yes, they will. So if I had a mixture of cis 2-pentene and trans 2-pentene, I could separate them. Right? They are going to have different structural properties. Okay, and these are not conformations, right? Conformations come from free rotations. These are not conformations, right? These are locked. The trans and the cis, it's not like it's alternating back and forth, right? This is locked in place because that bond is different from that bond. Okay. Right, so here's boiling point data. There's the cis boiling point of +4, +1, right? They're both gases at room temperature, but if you get to a low enough temperature, you could separate them based on boiling point. And again, you can only draw it based on how, you can only determine this based on how it's drawn. If I gave you this, the name's just 1-pentene, right? Because I haven't drawn it in such a way to show cis or trans, right? But if I gave you something like this, well, now I can tell cis and trans, right? And now I can tell cis and trans. Also, if the double bond is on carbon 1, is it going to be possible to have cis and trans? Because think about when you flush this out, hydrogen, hydrogen. Is one of those going to be bulkier than the other? No. So you're not going to have cis trans if the double bond's on carbon 1. Doesn't make sense because they're going to be identical. It's the same. So you wouldn't even have cis trans on 1-pentene. All right, so take a second and name this one. Be careful is all I advise. So when we name this molecule, we've got to ask ourselves a lot of questions. Question number 1 is, how many times is she going to raise and lower that screen? Where do we number from, the left or from the right? From the left, right? Okay, so we're going 1, 2, 3, 4, 5, or 4, 5, 6, 7. We're counting to 7, right? So what does that mean that this is? That's a substituent, right? Good. What kind of group is it? It's a methyl group. Okay. Now we need to ask ourselves, because of how this is drawn, is it cis or is it trans? Right? So we're comparing these two halves, which is bulkier. The top is bulkier, right? And I'm comparing these two, which is bulkier, the top or the bottom? The bottom. So does that make it cis or trans? Trans, right. So this would be trans. And then what? Do I have a substituent?
Yeah, 4-methyl.
4-methyl. Then what?
3-heptene.
Right. And just a reminder, if you're doing it the other way, it'd be trans 4-methyl hept 3. Right. Do we see how to do this one? See how we figured out that it was trans? A lot of students miss substituents when they're drawn this way because they just get so focused on deciding is it cis or is it trans and they forget to put the...
So 1 on 3 is that one?
This?
Yeah.
No, that's just the hydrogen. Yeah, that's just part of the alkene. So leaving off the trans, leaving off the location of the double bond, forgetting substituents, those are the most common mistakes I see with these kinds of molecules. I'm just going to try leaving it down. Does it create too much of a glare if I leave it? Okay. All right, if we were doing this one, I won't pause the recording. Let's just do it together. Do we have any substituents this time? Where are they? Are these substituents or is it just the chain? No substituents, right? Because if they were going to be substituents, they'd be right here. You're replacing one of those hydrogens with the substituents. There are no substituents here. So we just need to number whether we go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6 is irrelevant. Right? So 1, 2, 3, 4, 5, 6. Okay, is this cis or is this trans? This is cis, right? Because the two bulkiest parts are on the same side. So this is cis 3 hexene, right? Or cis hex 3 ene. Do you agree? Okay, so based on these drawings, can you tell cis trans? Can you tell if one's cis or one's trans just by the way I've drawn that for you? No, no. Now when you take organic, you'll learn something called EZ nomenclature, E and Z, but that's not something we do in intro organic, so you don't have to worry about that in this class. So I'm going to pause this and let you try it. Let's see if we got these. Okay, so where are we going to start numbering? From here or from here?
Oh, yeah,
it does matter, right? So where are we going to number? On the bottom, are you sure? 1, 2, 3, that gives my substituent being on number 3, and my double bond being on 2. 1, 2, 3, 4. Right? If I number from here, let's just look at what you would get. That would be 3-chloro 2-butene, right? But if I number from the top, what's that going to give me? 2-chloro 2-butene. So which one's correct? The bottom one's correct, right? Why?
Oh, because are they both on 2?
Yeah, the double bond starts on 2 if I'm going this direction, starts on 2 if I'm going this direction. So that's numbering from the wrong side. Do you see why it's numbering from the top, not numbering from the bottom? Yep. All right, if we number this one, we're going to number from the left or from the right? From the left, right? So we'll say 1, 2, 3, 4, 5, 6, 7, 8. So we've got 2 methyl groups. So the name is what?
2, 6, 7,
right?
3,
octene, right? And if we were splitting the ending, it'd be 2,6-dimethyl oct 3. You good on this one? Okay. I think there are a couple more practices in here that are in the notes that I'm just going to skip because I think we're kind of getting redundant. Let's get over here to this. When we have molecules with greater than 1 double bond, so we've got more than 1 double bond, we need to have a way to name that. So if you've got 2 double bonds, it's blah, 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 right? That's the rest of the molecule, blah, blah, blah. Then you'd say your numbers, and then you'd say diene. If it's 3 double bonds, you'd say blah, 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 and then you'd say your numbers, and then you'd say triene. So, for instance, here's a diene, 2,4-hexadiene, right? Because there's a double bond on 2 and there's a double bond on 4. Or 1,4-pentadiene, double bond on 1, double bond on 4. Let's just pretend that there is a double bond right here as well. So then it would be 2,4,5-hexatriene, right? If you had 3 double bonds, you'd state the locations of all 3 and then call it a triene. Make sense? Diene has 2, triene has 3. So let's name these. I'll pause it. Let's try. Let's look at this one. Of course, the answer's right there. Did you get 2,5-nonadiene and 2,4-heptadiene? Yes, yes, yes. Double bond, state the location, and then the most common mistake students make, they'll say 2,5-nona or nonene or something like that. They'll forget the di. That's the most common mistakes. All right, let me pause it and let you try these. All right, let's go over these. So, when we're numbering, we need to number, we have some options, right? We could number from the top, or we can number from the bottom, right? This isn't a carbon, that's just a bromine. So are we numbering from the top or from the bottom? 1, 2, or 1, 2. Right, why'd you pick bottom? Right, gives a priority. If you're going to get it on carbon 2, no matter what, you want to give the priority to the one with the substituents. Good. 1, 2, 3, 4, 5, 6. So what's the name of this? 1, 2, dibromo. Right? So they have 2 bromines. Then what? 2, 4, hexadiene. Right? 1, 2 dibromo, 2, 4 hexadiene. Yes. In this one, which way do we number? Right, because we can go 1, 2 and get a double bond on 2 with a substituent versus 1, 2, get a double bond on 2 without a substituent. Right? So we're going to go this way. So this would be what? 2, 4, di. What are those groups? Methyl. Then what? 2, 5, heptadiene. Right. 2, 4 dimethyl, 2, 5 heptadiene. Good. Okay. Now, when we're dealing with rings, carbon number 1 is where the double bond begins, right? Because that's the highest ranking thing. And again, we want to number in terms of clockwise versus counterclockwise. We want to give us the numbers that are lowest. And our numbering has to go through the double bond, okay? So for instance, if we had this, let's pretend I've got that. I can't go 1, 2. That doesn't make sense. The numbering has to go through the double bond. So it would be 1, 2, that way. Okay, it's got to go through the double bond. And I think in the notes I've got that exact example. So spoiler alert here. Yep, that exact example. All right, so how would you number this? There's one option, a random 4 on the screen. And then here's another option. All right, 3-methylcyclohexene versus 6-methylcyclohexene. The obvious choice is which one, left or right? One on the left, right? Now, why is it not 3-methyl-1-cyclohexene? Because by default, that's where the carbon number 1 is, right? You don't need to put the 1. Now, if there were 2 double bonds, yes, you would definitely need to put that. 1, 2, or 1, 2, or 1, 4, or whatever. All right, so let's name these. I'll give you a second to try it. Actually, pause. Okay, let's go over this now. If we're naming these, that's an I, by the way. Where's carbon number 1? It's right here, right? We're going to number counterclockwise. 1, 2, 3, 4, 5. So this is what? 3-iodo cyclo what? Pentene. Don't forget it's ene, right? Because if you call it 3-iodocyclopentane, that means that there's no double bond, and it wouldn't be on number 3, it'd be on number 1. For this one, we're going to number 1, 2, 3, 4, 5, 6, 7. So this is what? 4-ethyl cyclo what? 7-membered ring is a heptene. We agree? Again, the 1 isn't necessary because if it's an alkene in a ring, by definition, that's number 1. And the molecules that you'll be encountering in elementary organic are a lot less nasty than the ones you'll see when you get to full organic. So this is just intro level stuff. Okay, and again, going through the double bond, using the lowest of numbering. So for this example, we've got 2 substituents, right? We've got 2 substituents. I'm going to give you 2 choices. You pick the one that's correct. There's the option and the answer it produces. There's that option and the answer it produces. Which one do you pick, 5-3 or 4-6? The 5-3, right? 5-3 has the smaller numbers than 4-6. All right, you try this one. I'm going to pause it. All right, so let's see if we got the answer right. This is a 7-membered ring, and now we've got 2 substituents to deal with, right? So we need to pick carbon number 1, and we also need to pick which way we're numbering in terms of clockwise versus counterclockwise. Did you come up with the same answer I did? 3-ethyl 5-propyl cycloheptene. We good on this one? Okay, this time I'm giving you a skeleton notation, and I'm telling you that the red dot's a bromine atom. So why don't you try this one? Okay, that's a bromine atom and a methyl group, right? And there's our double bond. So there's what it looks like in skeleton notation. And we're numbering through the double bond using the lowest numbers possible. So we get 5-bromo-3-methyl cyclohexene. Okay, now again, when we have rings with more than one double bond, it's cyclo, whatever, triene, don't forget your numbers, right? And cyclo, whatever, don't forget your numbers, diene. Also, we want to go through the double bonds as well, using the lowest numbers as possible, and we're still going to put our substituent first if we have one. So if we have 2 double bonds, for instance, it would be 1,3-cycloheptadiene or 1,3,5-cycloheptatriene. Okay? And then if there were any substituents, they'd go in front of all that. Makes sense? Makes sense, makes sense. So here's an example. 3-methyl 1,4-cyclohexadiene. Does this make sense? We got a diene. Okay. So I'm going to pause it and let you try this one. All right, let's see what we did here. So we have to pick carbon number 1. We have to number through our double bond. There's only one answer that makes sense to be carbon number 1. Did you identify it? It's on the left, right, top, bottom. It's on the right, right? Because we have to number through the 2 double bonds before we start worrying about the substituent. So this is the only one that makes sense to be carbon number 1. Because I have to number through the double bonds before I start worrying about this substituent. If I numbered here, picked here, and went this direction, that doesn't make sense. If I picked here and went this direction, I'd number through the double bonds, but I would be giving this the smallest number possible, right? It'd be on carbon number 6. But here puts it on carbon number 5. So 5-chloro-1,3-hexadiene. All right, one more to try on the alkenes, and then we've got some alkynes to talk about quickly. So here, top is the only answer that makes sense, right? Numbering through both double bonds. Again, if you went any other direction, you would get bigger numbers than you needed to. Because if you pick this as carbon number 1, it'd be 1, 2, 3, 4, 5, as opposed to 1, 5, right? 1,5-dimethyl, 1,3-cyclopentadiene. Now again, like I just said, alkynes have at least one triple bond. It's linear during the triple bond, and we call it unsaturated, right, because it contains fewer than the number of hydrogens that an alkane does. C to the N, H to the 2N minus 2. And the only difference here is we change the suffix to YNE. So if you wanted to split the suffix, you could do that here. You could call it hex 1-ine. If you wanted to split that suffix, you could get the same splitting just like we did with alkenes, right? So there's the same suffix, hex 1-ine or 1-hexine. So here are 2 for you to try. And pause. Let's see what we got here. So on the top molecule, are we naming from the left or from the right? From the left, right. So this is 4-methyl-2-pentyne. We also could have named it 4-methyl-pent-2-ine, right? We could have split the suffix. Now these are the ones that get students in trouble. When I draw it like this, actually showing that it's linear during the double bond, a lot of students will miss this. They'll say, they'll give me all kinds of crazy numbering. There's a carbon here, and there's a carbon here, right? So it's 1, 2, 3, 4, 5. Students goof up with this if I draw it linear, because they, I don't know, something to do with the eye, visual illusion, right? There are 2 carbons right here, otherwise there couldn't be a double bond. So 2-pentyne. Make sense? Make sense? All right, let's name this one. All right. We're numbering from the left or from the right? 1, 2, 3 versus 1, 2, 3. We're going to get the same number on the triple bond, so we number to give priority to the from the left, right? So it'd be 2-bromo-3-hexine. All right, here's another one for you. All right, we got options here. Identifying the longest parent chain and then numbering to give rank to the substituents. We number from the, we could have numbered from the bottom here, right? 1, 2, 3, or 1, 2, 3. We'd have got the same answer either way. We've got an ethyl group on carbon 6. So 3,6-diethyl, 4-nonine. And I think the last one, is, yeah, dealing with aromatics, which gets its own lecture, so we're just going to skip over that because this is coming up later. And that's something for, that's an old slide. So here are some problems just to practice. We're going to be doing more of this week, so if you want to pause the video and try these on your own, you're welcome to. But we're going to be doing enrichment this week, so on-campus students don't really have to worry about it. And that's where we're going to stop for today.